Okay, good afternoon, guys. So we're nearing the end of the course, which I'm sure everyone is happy to hear. So good job on that. One thing we do around this time, something you've probably already got an email about, is online teaching evaluations. So this course, we do the teaching evaluations online. This is something that's been happening the last few years at Carleton. So starting last week, probably on Wednesday I think is when they started, they sent out an email inviting you to complete this. The way it works is you just follow the link in the email and you fill it out. Online evaluation is confidential and anonymous. So the only people who will see it are the people responsible for my job and me. And they'll have no idea who you are. It's anonymous unless you decide to write your name for some reason, which you certainly don't have to do. These things, maybe students don't realize, these things really do matter. These make a big difference, so I'll be honest with you and tell you how it works. So the numerical rankings that you give instructors in each category from 1 to 5, those play a huge role in decisions made about the careers of your various professors, so do take that seriously and give appropriate feedback. The comments you write are only read by the professors. Those aren't read by anyone else, so those don't factor into career decisions. They're still really important to us, and I pay very close attention to the comments that I get. So I would love it if you guys gave me lots of feedback about how this class is going. I'd love to hear what you think of, using the tablet versus more traditional slides or working with the Blackboard, what you guys think about the YouTube channel, which seems to have mostly positive feedback. If you guys have other ideas of stuff I could put on there, so one idea that's been floating around is maybe doing assignment solutions as a YouTube video instead of just a PDF. So ideas like that, those are things I'd really like to hear about. Any ideas you guys have for improvements for this course, I'm all ears, because I know this is a really challenging course. And I really want to do everything I can to make it better for you guys. And if you have any ideas, I'd love to hear it. So please do go ahead and do those evaluations and try to come up with some good feedback. That's the thing in my mind that makes the biggest difference. So I think you have until April 8th to do that or something like that. So where we are in the course now, we have today's lecture, Thursday's lecture, and then Tuesday's lecture. And then we're done. So assignment 3 is being returned during the tutorials this week, so do take a look at that. Assignment 4, you have until the 8th to finish. That obviously you won't be able to get back into tutorials. You will be able to collect it from my office, but there's no guarantee that it will be marked in time for the exam. We'll do our best, but it's unlikely that it will be marked by the exam. But you'll have access to the solution, so hopefully that's okay. Test 3 is still being marked. It does take a while, unfortunately, but that's just the nature of having a large class. I'm hoping to get those back to you in the tutorials next week. Next week, by the way, is the last week of classes. April 8th, which is a Wednesday, is really a Friday. So you follow a Friday schedule. So if you have your tutorial on a Friday, it's really on Wednesday the 8th. That's the last one. And that's where you'll get your test back. I'm not going to post questions to work on for next week. You guys can just work on your assignment in the tutorials, ask the TAs any study questions you might have, and get your tests back. Okay, so any questions about how the last week and a half is going to work? Yeah?
Is Tuesday going to be exam review then?
Yeah, our last class on Tuesday, I might have to finish up maybe 10 to 15 minutes of content, but the bulk of it will be exam review, and it is a thorough exam review, so I suggest you do not miss that class. The way it'll work is I'll cover the format of the final exam, and then give you a long list of the kinds of questions you'll see in the exam. So I'm not going to give you a full sample exam like I do for the tests, because that would be an enormous file that would take a great deal of time to work out. But I will give you a long list of the kinds of questions you'll see, and it's fairly reflective of how the exam is. So we'll have a long review lecture, and then I'll open it up to questions after that next week. Any other questions? All right, so let's jump back in. Last time we started talking about adjacency and degree, talked about some special graphs, subgraphs, connectivity, and the last thing we talked about were these cut vertices and cut edges. So remember, a cut vertex is a vertex such that if you remove it and all of the edges incident on it, then the graph becomes disconnected. So it goes from one connected component to two or more. And a cut edge is an edge such that if you remove it, it disconnects the remaining graph. So you go from one connected component to two or more connected components. Is that okay? So that's where we were last time. What I'd like to do this time is resume this discussion about connectivity. But if you remember last time, I said the discussion of connectivity was only in the case of undirected graphs. But you can still talk about connectivity in directed graphs. Oops, wrong color. So we can also talk about connectivity in directed graphs. And in this case, there's really two types of connectivity, right? You can say it's connected if you can get from any vertex to any other vertex, where get now means following the arrows. That would be one type of connectivity. And then there's another type of connectivity that says, okay, well, maybe you can't get from any vertex to any other vertex if you follow the directions of the arrows, but maybe there's a path if you ignore the directions of the arrows. So that feels like a weaker kind of connectivity, right? You have to ignore something to make it happen. And in fact, that's exactly what we call it. We call it weakly connected versus strongly connected. So a graph is strongly connected, a directed graph, I should say, is strongly connected if there is a path from A to B and from B to A for every pair of vertices A and B. So pick any two vertices in your directed graph, and there's definitely a path between them. And remember, paths have to respect the directions of the edges, right? They can only go along the edge in the direction that it is directed. All right. Another notion is a weakly connected graph. So a directed graph is weakly connected if the graph is connected when you ignore the directions of the edges. So what we say is that the underlying undirected graph is connected. So every directed graph has an undirected version, and you get it by erasing all of the arrows, so you just have undirected edges. If that underlying graph is connected, we say the directed graph is weakly connected. Okay, so when you want to figure out, is a directed graph connected? Well, first you need to decide, are you talking strongly connected or weakly connected? It's easy to check if it's weakly connected. It's sometimes a bit more work to check if it's strongly connected. So I'll do an example here. Let's say we have a graph that looks like this. This is A, B, C, D, and E. and I'm going to have edges that look like this. So I want to know, is this graph, first of all, is it weakly connected?
Yes.
Yeah, if I ignore all of the arrows and just look at the edges, so the underlying undirected graph, it's definitely connected, right? There's a path from every vertex to every other vertex. Is this graph strongly connected? So it is, but it's maybe a little bit harder to see. So let's go through. If I'm sitting at A, can I get to B? Yes, I just walk to B. Can I get to C? Yes, I follow AB, then BC. Can I get to D? I go AB, BD. Can I get to E? Yes, I go all the way around AB, BD, DE. So from A, I can reach everything. But of course, that's not it. I also need to do that same check for the other ones. In this particular graph, it's not too hard to see that it's going to be strongly connected because it sort of has this kind of circular pattern happening. Yeah?
In order for a graph to be strongly connected, do you have to be able to get from a node back to itself?
Yeah, so any pair of nodes which could include the case that you would want to get back to yourself. Okay, let's see another. So I'll say what this is. This is weakly and strongly connected. So if a graph is strongly connected, is it automatically weakly connected?
Yes.
Yeah, it's going to have to be. All right, so let's do the same graph, except I will change some of the directions of the edges. So I'll say A, B, C, D, E. E will go to A, B will go to A, D will go to B, D will go to E, B goes to C, and C goes to D. So is this graph going to be weakly connected? Well, yes, because the underlying undirected graph is exactly the same as the previous one. It doesn't matter which direction the arrows go. So this is weakly connected. Is this thing strongly connected, though?
No.
No, and the way you show that is you give two vertices such that there's no path between them. So A and B, for example, has no path between those two vertices because once you're at A, you can't possibly leave A. So this is not strongly connected. Is that difference clear? All right. So that's what I want to say about connectivity for now. So now we're going to move on to the next thing about graphs. We've got a lot of definitions for what graphs are, but we haven't really done a lot with them yet. So now we're going to start doing things with them. The first thing I want to talk about is depth first search. And this is commonly abbreviated DFS. So the idea behind this is the following. Suppose that you have some graph. If you've gone to all the trouble of representing this graph and storing this graph, presumably you're going to want to do something with it. And the operations you do on it usually are somehow related to moving around it or exploring it. So I'll give you some examples. So suppose you are trying to explore a graph. That sounds kind of weird until you see some examples. So maybe you want to see what computers are connected to a network. All right, so maybe you have a home network and you have a bunch of machines on it, and you want to know the name of each machine. So what you have is a graph And the graph has a vertex for every machine in your network, and an edge if those machines are connected in whatever way. And now you want to walk around that graph such that you visit every single machine and maybe output its name so the user can get a list of all the machines on that network. You might also want to see, say, visit different cities that are connected by flights. Right, so if you're taking Comp 1406 with me, we did an example a lot like this. You might have a vertex for every airport, and two airports are connected if there's a direct flight between them. And now you're an airline and you want to list all of these cities you can get to from some starting point. Well, you are going to have to walk around that graph, crossing those edges and somehow keeping track of what cities you visited before and which ones you haven't. So there's a lot of examples like this where you want to somehow walk around a graph. But it's not too hard to see that you can't just iterate through the vertex set, because that doesn't take into account the edges. And you can't just iterate through the edge set because that doesn't take into account the vertices. So you need to do a little bit more work than that. You need to somehow travel around the graph in an orderly way. And by orderly, I mean you need to keep track somehow of where you've been. Because if you don't do that, you could just be sitting in a cycle. And you could keep walking around that cycle forever and ever and ever. And that would be bad, because that would basically amount to getting lost while exploring the graph, and we don't want that. So the question of doing these searches is, how do you explore a graph in an orderly way? And orderly means in such a way that you don't get lost. So there's a few ways to do this. There's two that I'm going to talk about in this course. It's depth first search and breadth first search. The first one is depth first search. So the idea is the following. What we'll do is we'll say initially we haven't visited anything. So we'll mark all vertices as unvisited. And after that, we'll start somewhere in the graph. And we don't care where. So all I want to do is walk around this graph. So we start at an arbitrary vertex, and then we go to some neighbor that we haven't already visited. And the idea of doing it this way is this will ensure that we will never walk around in a loop over and over and over again. Because once we've visited a vertex, we're not going to visit it again, kind of. So we start at an arbitrary vertex, and we go to an unvisited neighbor of that vertex. Oops. And once we're there, we do the same thing. And we keep doing that until we've seen all unvisited neighbors. Okay? And once we've done that, we go back. So we go back up the chain. This seems a little bit weird until you see an example, and then hopefully it'll be pretty clear what's going on. So this technique is called depth first search. And we'll almost always just say DFS. This comes up a lot in algorithms classes. Anytime you're dealing with a graph, you should think to yourself, can I solve this problem by doing a depth-first search? And you'd be surprised at how often the answer is yes. So I'm going to make a graph, and I'm going to show you how a depth-first search runs on it. So this is kind of a bigger graph, so you can actually see what's going on. And I'm going to do this for the undirected case, but it's not too much more work to do it in the directed case. So this is my graph. This is what I'm doing. And initially, so the idea says initially, all vertices are unvisited. So I'm going to say if there's no notation, it's unvisited. So we start at an arbitrary vertex. Doesn't matter which one you pick. I'm going to start at F. So F is now officially visited, and I'm going to make a blue circle around things when they're visited. Okay, so now I start walking along this graph. So I'm currently at F, and now I need to go to an unvisited neighbor. So let's say, I don't know, let's say E. E is an unvisited neighbor, so I'm going to highlight the edge that I walk on. So that's an unvisited neighbor, so now I visit it. So now E is visited. And now I repeat. I go to an unvisited neighbor, and I visit it. So maybe C is the neighbor I pick. Right? There's lots of different choices I could make here. I'm just showing you one example. So I walk over to C. And now C has been visited. All right, so now I continue. I go to an unvisited neighbor of C. So let's say A. A is an unvisited neighbor of C. So I walk along that edge, get to A, and now A has been visited. So far, so good? All right, so now I'm kind of stuck. Right? Now I'm sitting at A, and A does not have any unvisited neighbors. Right? The only neighbor of A is C, and C is already visited. So I go and look at my steps, and step 4 was repeat until all unvisited neighbors have been seen. So I've just done this. So step 5 says to go back. So I'm currently at A, and now I go back to C. So I go back to C. Question? You go back to the one you came from. So I went from C to A, so when I go back to C. So like if there was another vertex like up here. So I would go back to A first, see there was nothing else, and then go back to C. All right, so now I'm at C, so I do the same thing again. I go to an unvisited neighbor of C. Well, the only unvisited neighbor of C is B. So I go to B. I've now visited B. I look for an unvisited neighbor of B, and unfortunately there are none. So that means I walk back from B to C. I look for an unvisited neighbor of C, and I find that there are none. So I walk back to E. I look for an unvisited neighbor of E, and there is one. There's D. So I go over and I visit D. So now I'm sitting at D, and I would like to go to an unvisited neighbor of D. Unfortunately, there is not one. So there is this edge here that I'll put in green, and I can't go over that edge because it leads to something that's already visited. So I can't follow that edge. So all I can do is go back from D to E. I walk back along that edge. And now I look for an unvisited neighbor of E, and I see that there are none, so I have no choice but to go back to F. So now I'm sitting at F, and I look for an unvisited neighbor. So let's say G. So I walk down to G, and I visit G. Now I look for an unvisited neighbor of G. H is such a neighbor. So I walk over to H. I look for an unvisited neighbor of H. Let's say I. I visit I. And now I'm stuck, so I have no choice but to walk back to H and look for another unvisited neighbor. K is an unvisited neighbor. So I walk to K, and then I walk to J. And now K and J are both visited. And now I'm stuck at J, so I walk back to K. I'm stuck at K, so I walk back to H. At H, I kind of maybe want to go to F, but of course F is already visited, so I can't actually go that way. So the only thing I can do is walk back to G, and the only thing I can do there is walk back to F. And now F has no more unvisited neighbors, and F is where I started. So I'm done. Right? I got back to where I started. There's no more choices to make, so I'm finished at this point. So is it clear what the algorithm here is? This makes sense? I'd like to visit all of the vertices in the graph. That's what I'd like to do. But I'd like to do it in such a way that I visit vertices that are next to vertices I've visited. So I sort of increase the area I've explored. Right? If you wanted to explore a city that you were visiting, you couldn't just teleport to every intersection. Right? You would start somewhere in the city, and you would start to walk around. And it's not too hard to see that if you were exploring a city, you shouldn't just start walking in random directions and hoping for the best, because it's very easy to get lost. The way that translates here is if you get lost, then you have no way of knowing if you're walking around a cycle infinitely many times. So that's the danger here. You could get lost, and lost means stuck in an infinite loop maybe. That's why we want to do it in an orderly way. Yep?
So it seems like there's kind of like a well-defined order to how this happens. So like is there any way to like a formal statement of what the order would be if I were like if I printed every new node when I visited it, would I know like it would go F and then E and then
No, so any time I picked between alternatives, I could have picked any one of those, and I would have gotten a different order that I visited the vertices in. That's okay and unavoidable. Yeah, so this doesn't give you a nice order on the vertices because there could be many orders that would work. Right? I usually break ties alphabetically, but there's no requirement to do so. I don't know what I did here. I just picked randomly. All right, so let's think about this this graph that we got a little bit. The yellow edges, so the highlighted ones, those have a property. What is the property that's interesting about those? They do make a simple graph, but it's stronger than that. Yep. It's a tree. That's definitely true. It's even stronger than that. Has one more property. Yep.
Is it like from the tree that's the longest, like the largest chain?
Close. You're on the right track. Yeah. The number of, it's very related to that, yes. The number of vertices. How many vertices does this tree have? Right, it has the exact same number as the original graph, which means this isn't just any tree, it's a spanning tree. So the yellow edges form a spanning tree. Oops, doing the other color. The yellow edges form a spanning tree, and they have to, because, this assumes that, that the graph is connected. But if the graph is connected, then the yellow edges form a spanning tree, and they have to because every node has to get visited by this at some point. Yeah?
What's
A
a spanning tree?
spanning tree is a subgraph that has the vertex set is the same as the original graph and is a tree. So you could have a subgraph that's a tree, but it doesn't visit every vertex.
A tree is just a graph that becomes a cycle.
Yes. All right, so the yellow edges form a spanning tree. It's spanning because all nodes are visited. So all vertices are visited, I should say. Just to be clear, vertices and nodes are used interchangeably. It's spanning because all vertices are visited. And why is it a tree? This particular one is it always going to be? Yeah.
Well, because it's a subgraph with no cycles.
Right, so why does it have cycles?
Because you can never, like you're either going to a new node or you're going back the way you came.
Exactly, right. So you never go from a vertex to a vertex you've already visited along a new edge. That never happens, because if you were going to do that, well, you wouldn't. You would actually just backtrack. So it's a tree because there are no cycles, because if you had a cycle, you would be visiting an already visited node. So that means a depth-first search is one way that you can get a spanning tree from a graph. And a spanning tree is something that comes in really handy when you're working with graph algorithms. And the reason is the following. Spanning trees don't have very many edges. So how many edges are there in this spanning tree? Right, there's 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 9 edges in that spanning tree. Did I miss one? Oh, between F and G. 10. Good. All right. I suppose. So there's 10 edges in this spanning tree. How many vertices are there? 11. Right? There's 11 vertices and 10 edges. Is this a coincidence? No. So anytime you have a tree on n vertices, that tree will have n minus 1 many edges. Does anyone see why that has to be the case? Yeah?
Well, I'm sort of looking at it inductively, so if you have 2 edges, or if you have 2 vertices, you have 1 edge between them. If you add a third vertex, you add 1 more edge in order for it to be a tree, right? You can't have 2 more edges, because that would be a cycle.
Right, so yeah, you're on the right track. So it basically goes like this. So the reason it's n minus 1 is because, well, could it be fewer than n minus 1, first of all?
No.
So if it's fewer than n minus 1, it wouldn't be connected anymore. So that's not a tree. Trees also have to be connected and not have cycles, I should clarify. So it definitely can't have fewer than n minus 1. And it can't have more than n minus 1, because if it did, then there would necessarily have to be a cycle somewhere. Okay, I'm not going to do a full proof of that, but you can sit down and hopefully convince yourself that that's the case. The nice thing is that regardless of how many edges there were in the original graph, so it could be as many as about n squared, in the spanning tree you only have n minus 1 if there's n vertices. And the nice thing about spanning trees is they still capture how to get from one vertex to another vertex. Right? So a lot of the time you can think of these spanning trees as like the backbone of a network. You could route, say, packets in a network along the spanning tree and everything would be fine. Right? If two vertices are connected in the original graph, well, they're still connected in the spanning tree, so the message will get there. Maybe it's not super efficient, but if your question is just about reachability, then the spanning tree answers it very nicely. All right, so that's depth first search. This has lots of applications. So things like finding paths between vertices, detecting circuits or cycles. So for example, you might want to write a program that takes a graph as input and figures out whether it has a circuit or a cycle, or maybe this is part of determining if it's a tree. You can use depth first search to answer that question. You can also use depth first search to find connected components. So the way you do this is you start a depth first search at every single vertex in the graph. Some of them will get to vertices that are already visited by a previous depth first search, but others won't, and that's because they're in a different connected component. So you can find those connected components using this. With a bit more work, you can use this to find cut vertices. So if you're careful about how you do this, you'll be able to use depth first search to find cut vertices, and that comes in handy if, I don't know, let's say you were planning a network and your network has a cut vertex. Well, maybe that's not great, because if that computer goes down, then your network becomes disconnected. That's probably not good, like a bit more redundancy. Yeah?
Is that related to the first application of finding circuit and cycle?
Yeah, it's a similar kind of idea, but in a different sort of application. And there's tons of AI applications here. AI meaning artificial intelligence. So the way AI works is, so let's say you're writing an AI to play some game. Well, the vertices in the graph are the different states the game can be in, and there's an edge between two vertices if you can move between them in a single move, something like that. So what DFS would do is it says, okay, well, let's start at the initial state of the game and explore and try to find a winning state. And the way that the computer wins the game is by making the moves corresponding to each one of those edges. Yeah?
So if you had like a lot more vertices,
Mm-hmm.
it would be like a lot different, more different states of the game, right?
Yeah. So that's actually very hard to model, because usually in graphs like that there's a huge, huge exponential number of vertices. Right? In a game like chess, it's not even really calculable. In checkers, we can officially do it, but it's still not pretty. In tic-tac-toe, it's very easy. Yeah?
So if you had like an AI for chess, you were trying to build it, you had it would be like the more vertices you had, the better your AI could be.
Yeah, so that's essentially the trade-off. We don't have, so the idea is that there's far too many vertices to fully map out the state space. So what we end up doing is having a bunch of vertices that take care of the state space when there aren't too many pieces left on the board. So that's why when the chess game gets closer to the end, a lot of the AIs are able to do really, really well, because they know exactly what moves will win them the game at that point. The problem, of course, is that they could have painted themselves into a corner already. This is one way to attack them. It's not the only way, but this is one way of doing it. Chess is a very, very hard game for computers to play. There's too many moves. In checkers, there's still a very large number of moves, but we have done that. That's the Chinook project. If you want to Google that. It's neat.
Is that how they did it? The guy a while back?
Right. So this relies on hoping for the best, basically. So you can't fully explore that graph because it's too big, but you can still do some smart things. And that's the idea behind that. So you don't know the exact sequence of winning moves in every game, but you have a pretty good idea of what works out most of the time. All right. So here's a free piece of information. How would you analyze this algorithm? Log of n. So why would you say log of n? Yeah.
Because it's going to be at least n times that you have to visit each of the nodes.
Yeah, that's a great observation to start with, for sure.
And it should be more because if you have to backtrack, you're adding one. But I don't know, that's all I got. I don't know why we didn't answer it.
Okay, so that's good. It seems like it might be, so for sure it's omega of n, because no matter what happens, you're visiting every vertex. Okay, so now it seems like maybe from each vertex you might want to visit every other vertex, and that would give you behavior that looks like n squared. Does anyone have any thoughts about this? Yeah?
So it looks like you go through each edge twice and there are n-1 edges.
Yeah, so, there aren't n-1 edges in the original graph, is the difference. But if you look at all of these edges in the graph, I have either a yellow on it and a red on it, or maybe I have a green on it and then nothing else on it. So if you look at each one of these edges, it's traversed at most twice, right? It could be by a yellow and a red, or maybe just by a green. So in the worst case, every edge would get traversed twice, which means I would need twice, the time I would need to be twice the number of edges. But I still need to visit every vertex at least once. So that would mean it's the number of vertices plus the number of edges. But if the graph is connected, there has to be at least as many edges as there are vertices, so it's really big O of the number of edges. Yeah.
I got a question.
Mm-hmm.
So when we're talking about, are we talking about the whole graph or just the tree?
The whole graph, because the problem that's given to you, the thing that you're computing, is based on the initial graph. So that's your input. You don't know the tree until you're finished.
And also, when you do the depth first search, aren't we only, like, we pick one arbitrary node
Yeah.
and then go to each other one off that?
Yeah.
And we don't change, like, we don't do all of them, you know what I mean? Like,
Well, so if you knew your graph was disconnected, you would then go and do the other ones too to see if they meet up later on.
yeah.
In a connected graph, no, you just start once and you're good. Other questions? Yeah.
This algorithm, it seems like really recursive, so it,
Yes, this is very well suited to recursion for sure, because whenever you do this backtracking, you want to go back to where you came from, and that's exactly the same really as returning from a function call. So this is very well suited to recursion.
is it possible to do it iteratively?
Yes, but then you need some kind of fancy data structures. Basically, you need a stack, and that stack exists to simulate recursion without actually doing it. Other questions? All right, so I want to talk about the other one now. The other one is breadth first search. So in depth first search, the idea behind the algorithm was to always go as deep as possible. Right? You always move to something you haven't seen before. Breadth first search says spread out evenly as your search continues. These are two sort of two opposing ideas. Depth first search says move as far away as you can from your starting point until you get stuck and then backtrack. Breadth first search says move gradually away from your starting point until you reach sort of the boundary of the world. Breadth first search is probably what you would do if you were exploring a city and were kind of cautious. right? You wouldn't go as far away from your hotel as possible and then try to make your way back. You would gradually explore a wider and wider area. So the idea is, instead of exploring, instead of always going as deep as possible, as in DFS, we could try to explore gradually at specific and increasing distances from the starting vertex. And doing this is called breadth-first search. And not surprisingly, this is abbreviated BFS. All right, so this is a little bit more complex in the description, but actually doing it I don't think is anyways. So the way it works is we're going to need to maintain some list of vertices we've seen so far. Okay? And initially, this just contains an arbitrary vertex. Right? And that's the same idea as last time. It's our starting point, if you like. And now we get into the algorithm. The algorithm says, add all adjacent vertices to the end of the list. And notice it's the end of the list. Now we take the first vertex off the list and visit it. And when we visit it, we add all of its unvisited neighbors to the end of the list. And now we repeat 3 and 4 until the list is empty. So it's really important to pay attention to when you're adding things at the end and removing things from the front. This, in fact, has a special name in data structures. Does anyone know what it is? It's a queue. So this is an important data structure. DFS, you do with a stack. BFS, you do with a queue. So if this seems weird, I'll do an example, and then hopefully it won't seem weird anymore. So here's my graph I'm going to do for this one. It's a little bit more grid-like. So this is A, B, C, D, E, F. I think I called this one G, H, I, J, K, M, L. And it's connected this way. All right, that's what our graph looks like. I'm just going to draw the labels off to the sides so they don't interfere here. There. All right, so I'd like to do a breadth first search of this graph, and I'm going to start at E. So I want to start at E. So what I do is I say, okay, keep a list of vertices seen so far. So I'm starting at E, and I want to add, so I'll start from the very beginning. The very beginning is I put my list over here, and initially it has E in it. And I'm just starting an E arbitrarily. You can start anywhere you like. So that's step one. Initially it contains an arbitrary vertex. So now I add all adjacent vertices to the end of the list. So the vertices that are adjacent to E are B, D, I, and F. B, D, I, F. So now I take the first vertex off the list, which is E, and I visit it. So E is right here, and I visit it. So now E has been visited, and I add all of its unvisited neighbors to the end of the list. So that's redundant in this case, because I've already done that. So maybe I can rewrite this pseudocode a little bit. Okay, so I've taken E off the end of the list, I've visited it, and now I repeat step 3. Step 3 says take the first vertex off the list and visit it. So the first vertex on this list is B, so I visit B. I was at E, now I'm at B. So I walk that edge. So now I visited B, and I add all of its unvisited neighbors to the end of the list. Its unvisited neighbors are A and C. I don't include E because I already visited E. So I add on A and C. And now B has been visited, so it's finished. So now I go to the first thing in the list, which is D. So I walk from E to D. Oops. Is it clear why I'm doing this walk from E? Is that okay? Okay. So now I visit D. Great. Now I add in the unvisited neighbors of D, which are A and H. Well, A is already in there, so I'm not going to add it again. I'm just going to add on H. Oops, wrong color. I'm just going to add in H. There's no point in putting A again. You could, but now you have to keep track of removing it the other time. Okay, so now I've finished with D, so I go to I. So I follow this edge to I, and now I is visited. And I add in the unvisited neighbors of I, which are H, K, and J. So I add those in. H is already in there, so I need to add K and J. That's okay? So now I'm finished with I. So I go to F. And now I'm there again from E, and F is now visited. And now I add in the unvisited neighbors of F. Those are C and J, but they're already in there, so everything's fine. Okay. Oh, yeah, G. Good catch. Oh, wrong color again. Okay, and you might notice something that's happening here. At this point, we've exhausted all of the neighbors of our start vertex. So I'm going to add a little bit of extra notation here to help me remember that. I'll do it in red. The start vertex, I'll say, is 0. And vertex D, B, F, and I are all 1s, because I followed one edge from my start vertex to get there. Does that make sense? So how is this going to continue? If we step back from the pseudocode for a second and just look at the pattern that's happening, what's going to happen next? Yep. So what do you mean I'd go to A? Oh, yeah, sorry, I forgot to cross off at. Yes, exactly. You would go to A. How would you get to A? Right, from B, because B is where you added it to the list. So now I have this edge to A. A is now visited, which is nice. And notice that it takes 2 edges to get from E to A. Okay, so what do I do next? Now A is done. Now I go to C. And I go to C from B. And now C is visited. And it also takes 2 edges to get from E to C. All right. So now I've taken care of C. And notice I don't have to add any more extra vertices because there were no unvisited vertices there. So now I do H. How did I get to H? From D. Yeah. So there is some other stuff. If you actually sat down and coded this thing, some other stuff needs to be kept track of.
But doesn't this mean that for every edge, you have to keep track of which edge got you to that edge?
Yeah, you're going to need to keep track of that somehow. There's a few ways of doing it, but that's the bottom line of which you'll need. So now I'm at H, and that took 2 edges to get there. And now I do the same thing for J, but before I do that, I have to add K to my Q. Oh, you're right, it already is there, sorry. Okay, so now I do J. I got the J from I. Sorry? No, I haven't done K yet, but that's further down, right? J. Oh, yeah, no, you're right. I haven't done K yet. So that's fine. I'll do K next. So now I visited K. K takes 2 edges. And now I add in M to my Q. So now I'm done with K. So I go to J. J I got to from F, or no, from I. So I add that. Now I visited J. And I visited it with distance 2. No, I have an I here and an F there. Yeah. Yeah, it is a little bit hard to see the way I've crossed them out. Okay, so continuing on. I already have a G, so I don't need that again. So now I take my, oh, sorry, I just did J, so that's done. Now I go to G. G's right here. Whoops, wrong color. G's right here. How did I get to G? Right, I got there through F. And it's not a coincidence that F's number is 1 and J's number is 2. So G now has number 2. And I add in L to my list, to my queue. And now G is done. Whoops. Now G is done. So now I take the next thing off of it, which is M. So I visit M, and I got there through K, and I had to because there's no other way to do that. So M has number 3. So now M is done, and now I go to L. and L, whoops, is now visited and has number 3. And now the list is empty, so I'm done. Yeah?
This is sort of like finding the shortest path to each node.
Yeah, this is going to be exactly finding the shortest path, where shortest path means the fewest number of edges. Right? So this doesn't take into account how long any of these edges are, it's just taking into account the number of edges. That's exactly what the red numbers are. Right? To get from E to E, well, I don't move at all, so I need to traverse 0 edges. To get from E to G, I need to traverse 2 edges. To get from E to C, I have to traverse 2 edges. There's some choices about which 2, right? There's 2 paths to do that. And that corresponds to the fact that I could have chosen to visit any one of E's 4 neighbors first. Yep?
So, a couple of things. Is this also a spanning tree?
That's a good question. So is this going to be a spanning tree? Okay, so is it going to be connected? For sure, right? I've visited every vertex. Is it ever going to have a cycle? No. So it's not, so I just mean the yellow edges. The yellow edges aren't going to have a cycle because if they did, I would be doing this thing where I'm at a visited vertex and I walk to a vertex that's already visited. So this thing is connected and it does not have any cycles and it visits every vertex in the original graph. So it is for sure a spanning tree. So let's write that down before we even go any further. So this also produces a spanning tree. Other questions? Okay, so let's make our second observation. Our second observation is that it also gives the length of the path with the fewest edges from the start node to any other node. So it seems like it matters where I start. So could I use this to get the length of the shortest path from, say, H to F? Is that going to always work? Yeah?
Could you add together from E to H?
So I could take the path from E to F and the path from E to H. In this case, that would give me a path of length 3. Unfortunately, that won't always be the shortest path. It will always be a path, so you'll get an upper bound on the length of the shortest path. But unfortunately, there are cases where this doesn't work out quite perfectly. Okay? That would happen in this example, for example, if I had an edge from H to E, but I visited D before I went across that edge. Even in that case, it would be okay in this graph. But there are cases where it's not. Yeah, that's a great example. Yeah, exactly. So the problem is that forcing yourself through E might not always give you the shortest path. Other questions or thoughts? Yeah.
Doing it on a complete graph would be probably really easy. It probably wouldn't be very easy to say. If you take a node, you can go to all the other nodes on the first try. And
Yes. And that makes sense because the distance from any node to any other node in a complete graph is 1. You can always follow an edge to any other node. But yes, the spanning tree you get looks like an asterisk, basically. It's a giant star. Other thoughts? So what you get, so notice I've said that this gives you the length of the path with the fewest edges, and that sometimes might be a shortest path, right? Not always. It depends on what you mean by shortest path. So if you're looking at just the number of, say you're talking about a computer network of some kind, if all you're concerned about is the number of hops between two machines, well then this is the shortest path. But maybe you have a bad connection between two machines and you'd rather not take that. Well, this doesn't take that into account. You need something else called weighted edges to deal with that. And that's a topic that we defer until a little bit later. We won't be covering general shortest paths in this course. But if all you're concerned about is the number of hops, then this is a reasonable way of computing shortest paths. The analysis of this one is a little bit trickier, so I'm not going to touch on that. So those are the two ways to explore graphs. Any questions about graph exploration? Yeah?
If a graph is spanning, is it necessarily a tree?
What do you mean? If a subgraph is spanning? No, it doesn't have to be a tree. So for example, the entire graph is a subgraph, and it's not going to be a tree if the original graph is in a tree. And similarly, if you remove one edge, it's probably not going to be a tree. Okay, so there are two topics left in this course. The first one is planarity. And the second one is graph coloring, which we'll get into next time. So the idea behind planarity is this. Sometimes it's really easy to get confused about a graph that you see a picture of. This is something that's easy. When is it probably easy to get confused by a graph? Yeah? If it's really big, okay. But it's still sometimes easy to reason about big graphs if they're drawn really well. Right? So I could have 1 million vertices on top, and each one is connected to just the next one. And it's still easy to reason about that because it's clearly just a line.
It's like big and complex.
Right. So what do you mean by complex?
Like many edges, and there's a lot of self-loops, and there's edges connected to the same vertices, whatnot.
Right. So a lot of edges plays a big role, but it's not just the sheer number of edges, right? It's how the edges are arranged. Yeah?
A lot of edges crossing each other.
Yeah, it's easy to get confused when a lot of edges cross each other. So even if we had a really big graph and we asked ourselves, is this vertex connected to this other vertex? That should be pretty easy to answer, right? You just follow the path, or follow the single line from one vertex to another vertex. But if there's a lot of edges crossing, this becomes hard. So let's say I want to know, is this edge, is this vertex U connected to this vertex V? That's pretty easy to figure out. I just follow that line. One thing I didn't tell you is that graph edges don't need to be straight lines. It's just as correct to draw it like this. That's the exact same graph, because remember, in graphs, all we care about is that the edges are connected to each other. The vertices are connected to each other. We don't care about how those connections look. And now let's say I had a bunch of edges all over my graph that looked like this. Now if I ask you, are U and V connected, it becomes a little bit tricky. Right? It's a lot of work to follow that edge through all of its twists and turns. In this setting, what's making it difficult is the fact that these edges all cross. If these edges didn't all cross, so if we had something like this, it still wouldn't be pretty, but at least we would be able to follow an edge all the way between two vertices. So all this to say, we kind of like it when edges don't cross. Right? The pictures look prettier when the edges don't cross. That's all I'm trying to say here. If many of the edges cross, it's difficult to determine which edge is going where. So it's often nicer to look at graphs where edges do not cross. So there's lots of ways to draw a graph, because remember, we just care about how the vertices are connected. We don't care what the edges look like, at least not for now. So here's an example. We all remember what K4 looks like. It's the complete graph on 4 vertices. And the way I drew it originally was like this. So let's say this is vertex 1, 2, 3, 4. This graph, I would argue, is not a nice drawing because 2 edges cross, right? There's a crossing right in the middle, right here. And crossings are bad. One possible reason is maybe now it kind of looks like maybe there's a vertex in the center, but there's not. It's just because 2 edges are crossing. There's not actually a vertex there. But in general, it's just confusing. So we ask ourselves, is there another better way of visualizing this? And in fact, there is. I submit to you that this is exactly the same graph. And to prove it, I'll label it. So in the graph on the left, 1 is connected to 2, 3, and 4. 2 is connected to 1, 4, and 3. 3 is connected to 1, 2, and 4. And 4 is connected to 1, 2, and 3. The exact same thing happens on the right graph. So these are exactly the same graph. It's just 2 different ways of drawing it. Right? It's exactly like how you could have 2 formulas in propositional logic that are logically equivalent, but written 2 different ways. The exact same thing is true about graphs. We only care about how the vertices are connected. We don't care about how the graph looks, except now we're starting to, because we don't want it to have edge crossings. Yeah? So yeah, this is in fact W3. But yeah, so K4 and W3 are the same graph. Right? 2 different ways of describing it. Just like K3 is the exact same thing as C3. The complete graph on 3 vertices is a triangle, and so is the cycle on 3 vertices. So even though these are drawn differently, they're essentially the same graph. And for our definition, they're exactly the same graph. They both have 4 vertices where each vertex is connected to every other vertex. All right, so there are multiple ways of drawing the same graph. That's the punchline here. And we like the drawing that doesn't have any edge crossings. And we call a graph planar if it can be drawn without any edge crossings. And it's really, really important, so important that I will both underline and highlight it, that you see this word can. So this thing right here, this is a planar graph. And that surprises a lot of people. This graph is planar, and it has to be, right? I just showed you that it can be drawn without edge crossings. Planar does not mean that it is drawn without edge crossings. It means that it is possible to draw it without edge crossings. So this graph, K4, it's planar. And it's planar because I could have drawn it like this, not that I did draw it like this. Is that distinction clear? Yeah?
All the complete graphs planar.
No. In fact, almost none of them are. Yeah. Yeah.
So what's the graph called that can't be drawn without the
If there's no drawing of it without crossing edges,
Yeah.
we say it's non-planar. Yeah, it's not a fancy term. Other questions? Okay, so it does make sense to talk about the drawing itself. If you draw it without any edge crossings, we say that drawing is a planar representation of the graph. So this is planar. And this thing here is the planar representation. So at the risk of confusing you, there is a term for a graph that is planar and is drawn in a planar fashion. And unfortunately, that term is plane. So this graph here is plane and planar. This graph here is planar, but not plane. I don't love that. It wasn't my idea, but this is how math is developed.
Wait, how do you spell plane?
Plane, like the surface. All right, so don't worry too much about that distinction in this course, but if you see plane, that's what it means. All right, so this example shows that K4 is planar. You wouldn't say K4 is plane. It only makes sense to say a drawing of a graph is plane. You don't say a graph is plane. So it seems like things are good, and maybe lots of things, or maybe even everything is planar. But in fact, not all graphs are planar. And my challenge for you is this thing here is K33. Turns out that that thing is not planar. So no matter how hard you try, you cannot draw that without edge crossings. And if you don't believe me, spend some time tonight trying to do it. So next time we'll pick up back here.